Hello, welcome to this video on Gravitation and Coulombs law, a review. I'm going to be doing this problem set, which should review gravitation and Coulombs law and electric fields. And I have some announcements. One, if this video is posted, that means I have successfully gotten permission from my teachers to continue making these videos. And two, I've decided until I get a pad or some instrument which will make my handwriting not terrible, that I will pre-write the work I would do in as best handwriting I can, and then explain walk. I think this will be. I think the same effect should be reached. So anyway, let's start with question one. The asteroid Icarus, discovered in 1949, was so named because of its highly eccentric elliptical orbit, brings it close to the Sun at perihelion. The eccentricity E of the ellipse is defined by the relation Rp equals A multiplied by 1 minus where Rp is the perihelion distance and A is the semi-major axis. Icarus has an eccentricity of 0.83 and a period of 1.1 years. So first I want to define three terms. One, eccentric. Eccentric means deviation from a circular path. So, an elliptical path, which is what they say. 2. Perihelion. Perihelion is the distance closest to the Sun, or whatever it's orbiting around, in this case the Sun. So, I have a diagram I will show you in a moment. And aphelion. Aphelion is the furthest from the Sun. So, let's go to my diagram. Here's my diagram. Here's the Sun. This planet Icarus is rotating in this elliptical orbit, and when it reaches right here, when it reaches right here, it is closest to the Sun, and this is the distance perihelion. I call it RP, but it's not necessarily a radius. In fact, it's not even a radius, but I'm going to call it radius perihelion, and then this distance right here is radius aphelion, the farthest distance from the Sun. It's when it reaches here. So this is the diagram. It says, determine the semi-major axis of the orbit of Icarus. So, first, what is the semi-major axis? So, it's a part of an ellipse, and if you know anything about ellipses, you know that the semi-major axis is this distance here, this A. It's not all the way to the Sun, it's to the center of the ellipse. So, the entire major axis is 2A. So, and by the way, semi-major, the major part means it's the longer distance, so the width, not the height. Or actually, not necessarily, but like this, the longer distance. So, determine the semi-major axis of the orbit of Icarus. So for this, we're going to have to use Kepler's third law, which I will read the definition from. Kepler's third law says, the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the Sun. So if you look up this formula, you will get the formula. Let's see. Actually, it's not here, but you will get t squared equals c multiplied by a cubed, or t squared equals 4 pi r squared over gm multiplied by a cubed. And actually, c is some constant, and the constant is equal to this right here. Where is my? Well, I guess I can't write anymore. Oh well. Well, this thing right here, this is the constant that they're talking about. So we want to solve for a, so we can just rearrange this. So I multiplied by the reciprocal, got this, took the cube root, got this. So now we have a, and we have everything we need actually. It gives us the period. We know the g constant. It gives us the mass of m is the mass of the object it rotates around. In this case, the Sun. Mass of the Sun is 1.989 times 10 to the 30 kilograms, and divided by 4 pi r squared. We know that. So here is this. This is the expanded expression, cube root, and you have to do years into. You have to bring it into seconds because g is in seconds. So if you want the units to cancel out and to get the right answer, you have to bring it to seconds. So multiply by 365 days. These days cancel. These hours cancel. The minutes cancel. Everything cancels, and then you'll get this answer. Or depending on your data or whatever numbers they give you, you might get a different answer. This is the answer I got, and I checked this in the calculator. This is correct. Now, determine the perihelion and aphelion distances from the orbit of the cars. This part is really easy. They give you the formula right here. Radius or distance perihelion equals a multiplied by 1 minus e. They give you e. We just solved for a, so we know a from part A. We also know e from the problem. So RP equals a times 1 minus e. This is a, this is 1 minus e, and this is RP. So that's how we get that. Now, for part B, or not part B, for the second part, the aphelion distance, as I said earlier, as you can see, RA plus RP, the radius aphelion plus the radius perihelion, should be equal to this entire axis, this entire major axis, which is equal to 2 times the semi-major axis, which therefore means that you have this formula right here. RP plus RA equals 2 semi-major axis A. You can solve for RA, and you know A, and you just solved for RP, so then you get this answer right here, which is right here. Okay, number 2. Problems 1 and 5, so I have to go to I did these in different things. Alright. A satellite with mass 330 kg moves in a circular orbit of this many meters above the Earth's surface. What is the gravitational force on the satellite? So, there's a gravitational force formula right here. Fg, gravitational, equals g times the mass of the Earth times the mass of the object divided by the distance squared. So, that's very easy. You have, g right here, 6.67 times 10 to the minus 11 meters cubed, kilograms to the minus 2, kilograms to minus 1, seconds to the minus 2. You know mass of the Earth. Well, if you look it up, it's 5.972 times 10 to the 24th kg. You know the mass of the satellite. It tells you 333 kg. And for the radius, I actually did not get this question right initially because I just used this distance as the radius. But you actually have to factor in the Earth's radius, which is 6.371 million meters. So I did this radius, the Earth's radius, plus its distance away, and I did that all squared because that is the distance. And then I got the right answer. For the velocity, the speed of the satellite, doesn't ask you for direction. For the speed, there's a formula called the speed in the orbit. There's 2 different speed formulas. Escape velocity, and then velocity of the orbit. Now they are very different. Actually, they're similar, but they're different. So this is the orbit one. There's no 2 here because the escape has a 2. So v equals square root of g times m, which is the m central, as in what it's rotating around, over radius. So g right here, we know g. M we know because we looked it up, and then r we know because we know r. It's what they give us plus the radius of the Earth, and then that equals this many meters. This many meters per second, which you can multiply by 1 kilometer, and then you can divide by 1,000 meters. Like, because you multiply by this ratio, and then you can get it into kilometers per second, which is what the problem asks. What is the period of the satellite? Well, there's the period formula. I didn't copy paste the red thing, but the period formula is T equals 2 pi r over velocity. Actually, I think this is from an earlier unit, but it still applies here. So we know r, we know velocity. 2 pi times r times over velocity, and then you get the right answer. But one thing I wanted to point out is to make sure that v and r are both in either m or both in km. I did it both in m because I like m, or meters. I had this in my calculator before I divided by 1,000, and then I solved for this radius. I had always done in meters because you had to. But if you wanted to use kilometers on the bottom, the velocity in kilometers, you have to convert this to kilometers, the radius too, because you want the units to cancel, and for everything to just become seconds. So you have to do that. And then of course at the end you multiply by these ratios. 60 seconds in a minute 60 minutes in an hour, and then you can get how many hours it is, because it asks for hours. And that's what I got. Okay, number 3. 3. Two concentric uniform thin spherical shells have masses m1 and m2 and radii a and 2a as shown in the figure below. Use any variable or symbol stated as necessary. For problem A. What is the magnitude of the gravitational force on a point particle of mass m not shown, located at a distance of 4a from the center of the shells? So let's take a look at what we're looking at. Alright. So I actually need to fix something for like 1 second. Where is my typing? How do I type stuff? Well, I would like to type stuff, but never mind. Anyway, so for number 3. So a distance of 4a away from the shells. So 4a is somewhere out here. So what will be affecting this point 4a away? So let's look at this. So first we know the formula. F of g equals g times the m1 times m2 over distance squared. So m1 we know, because it gives us m1 right here. It says use this m. But what is this m2? What is affecting this m1, which is 4a away? Well, both this m. Well, I said m1. I messed up. Sorry. This when I said m1, I meant this m out here. Let's call it mass mo, mass of the object. So what is affecting this mass of the object? Both this m1 and this m2. So what is the total mass of that? It's just m1 plus m2. So m1 plus m2. And then what is the distance? Well, you have to take the distance away from the center. So you will get it 4a. So 4a is the distance. If 4a is the distance, then 4a squared will be 16, and then you have to square the a part 2. 16a squared, and that's how I got this answer. Now, I just wanted to say that you could have done this separately. What you could have done, if I had a pen working, which I don't know, my pen disappeared, I'm sorry, that you could have done it in 2 different ways. You could have done it, I wish I had my pen. Where is this? Drawing, where's my drawing? This is really disappointing. I don't have my pen. Where is my pen? I 1 second, I'm sorry. Can I draw now? Can I ever draw? Where's did I hide it? Is there any way oh, I found it. I found it. It's right there. Alright, we're back here. So what you could have done instead of what I did, you could have done the sum of the forces, and they're both in the same direction, by the way. Sum of the forces is F net equals F1 with this vector hat plus F2 with this vector hat dot dot dot. So then what would F1 be? So F1 would be G M, and then M as in lowercase. Sorry, let me do this. Lowercase m, G lowercase m times mass 1 all over 16a squared. And then F2, because we're I'm just gonna directly add them to save energy. F2 you would, because you want to add F1 and F2, would be G M1, sorry, G lowercase m m2 over 16a squared, because you have to take it from the center, and you know the center is right there, 16a squared. So given this actually just implies this. So you could think about it both ways. That was the point I wanted to make, because you know, distributed property. Yeah. So that's the answer to this one. Okay. What is the magnitude of the gravitational force particle of point mass m located 1.4 a from the center? Okay, and by the way, A is just some constant thing. And so let me erase this and erase this and erase this. So now, if you guys haven't looked at the answer by accident already, you notice M1 is the only one up here representing the masses affecting it. And that is because only M1 affects this object, this random point. Because you see, according to the problem, this big guy M2 is 2a away. So then that means the point mass M is somewhere in between M2 and the outer layer of M1. But because it's inside M2, the M2 doesn't have a gravitational force on it. So the only thing affecting a gravitational force on it is M1. So just M1 here. And then the radius, it tells you 1.4a. 1.4 squared is 1.69. So that's how I got this answer. And then the G and the M are the same because you need those, right? Alright. So, and then, darn. For the last part, what is the magnitude of the gravitational force on a point mass m located at a distance of 0.8a from the center? So now this is similar to part B. 0.8a is less than the first mass. It's somewhere right here, inside the first mass, inside the second mass. So neither mass 1 nor mass 2 will actually affect any force on it because it's inside them. Like, so if something comes out here, then this guy is gonna put a gravitational force on it. But if it's inside, that just doesn't happen. It's just the laws of physics. So because there's no force to add. This formula is not even applicable because there is no force. So the force is just immediately 0, which is what the answer is. Okay, so I think we're making good time. Problem 4. Okay, down here to problem 4. And note why this problem confused me. I will come back to why this problem confused me, because it did confuse me very much, and I'm not happy about that. Anyway, so I mentioned the orbit velocity formula, but in this problem, we actually use the escape velocity formula. So let me read the problem. A satellite is circling the moon, radius 1,700 kilometers, close to the surface at a speed v. The projectile is launched vertically up from the moon's surface at the same initial speed v. How high will the projectile rise? Take m and m as the mass of the satellite and moon respectively. Okay, so escape velocity. Let's first start with the escape velocity formula. And I'm defining the capital M as the mass of the moon, lowercase m as the mass of the object. Okay? And then we have to use the energy conservation formula. I think there's probably another way, but this one is the easiest. So EMEC is conserved. You have this equation right here. Initial kinetic energy plus initial gravitation potential energy is equal to final kinetic energy plus final gravitation energy. And then you have the 1/2s. 1/2 v initial squared plus mg h initial equals 1/2 v final mv final squared plus, we can actually cancel all these m's because we don't need these m's. These m's cancel too. But as you can see, it starts at h0, so h initial is actually 0. It's nothing. You don't need to worry about that. And then v final is nothing. It does probably have some sort of orbital velocity, but we're talking about upward velocity. Like, what I mean is that they're two different velocities, so that's why the v final is here. So it's launching up. It's launching up here, and this is the atmosphere, and then it stops. Its velocity becomes 0, and then on a completely unrelated note, it starts orbiting with some different velocity. But its velocity for this conservation of energy problem is 0 at this point. So then we don't need to worry about that. And then we have this equation right here. 1/2 mv squared. I canceled the m's. So 1/2 v squared equals gh. H final. But I'm just going to call it h. So then I canceled them here too. So then rearranging the equation for h, we get h equals v squared over 2g. So let's use the local g formula. Like for Earth, rg 9.81 meters per second squared is equal to the universal gravitation constant times the mass of the Earth divided by the radius squared. But if we're at the Earth's surface, then we just use the radius of the Earth. But if we're higher up, then the gravity is actually be different. But for this, I think we're on the moon, so m is the mass of the moon, g is the universal gravitation constant, and then r is the radius that they give us, which is 1700 kilometers. Well, that glitched a bit. 1700 kilometers. So then we have we substitute in this formula for local g into this h, and then we put it down there. And then what I did is I put it out here. Then this r cancels with this. These gm's cancel. The 2's cancel, and it ends up just being r, which is 1700 kilometers. Now, I said why this problem confused me is because it said take m and m as the masses of the satellite and the moon respectively. So then what is this mn? Is that this? Turns out that this mn is actually a megameter, which I did not know existed, but it is 1,000,000 meters or 1,000 kilometers. And then if you multiply these things, you'll get 1.7 megameters or something different if you have a different like planet or whatever. So number 5. Let me go to number 5. Number 5. I have a Q note here. I will explain that in a moment. Let me read the problem. An electron has an initial velocity of 1 times 10 to the 6 meters per second in the x direction. It enters a uniform electric field of in the y direction 400 Newton coulombs, which is in the y direction. Find the acceleration of the electron. All right. So, all right, let me say the Q note first. So, as you can see in this formula, I haven't put a vector hat on Q. I think I did so in my last video, but the reason I didn't do it this time is because I looked up Q is neither a scalar nor a vector. It has magnitude and it has a sign, which is its charge, but it's neither a scalar nor a vector, so that's why. Anyway. So for this problem, we have to use this formula. This formula here. E equals F over Q. So then you can multiply the Q to this side. EQ equals MA, which is F. And don't forget the vector hats. So we know Q because it says an electron, and then an electron's charge is negative 1.6 times 10 to the minus 19 coulombs. We know m because it's also a mass of an electron, which is 1.9 something times 10 to the minus 31 kilograms. And so we know q, we know m, we know e, so we can just solve for a. And remember, a is in the j direction too, because since this field is in the y direction, the positive y direction, we have this frame of reference. It makes intuitional sense that the acceleration is going to be in the y direction as well. So it turns out that it is. And then if you calculate that, you will get this for these numbers. I don't know about this. So this is what A says. There is no x direction acceleration. That is true. And is this part B? I think so. How long does it take the electron to travel 10 centimeters in the x direction of the field? Well, there's no x direction whatsoever, so we can just use the kinematic formula. X equals x initial plus v initial x times t plus 1/2 a initial x times t squared. So it starts at 0, so that's 0. It has no acceleration in the x direction, but I believe it does have velocity. And it says the velocity isn't only at the x direction, so we don't have to do any cosine or sine theta, which doesn't exist. So Because this is 0, you get rid of this, you get rid of this. You get x equals v initial x, which is actually just v because it's in the x direction already, times t. X over v initial x equals t. And then x is 0.1 meters because it says it's 10 centimeters. And then v initial is this. And then you'll get the answer in seconds. But it's asking for micro, nanoseconds. Let me see. It is a microsecond. It's asking for microsecond, and there's a million microseconds in a second. So you can just multiply by this ratio, and then you'll get how many microseconds there was. And for mine, it happened to be 0.1 microseconds. By how much and in what direction is the electron deflected after traveling 10 centimeters in the x direction? To indicate direction, use both negative for down and positive for upward. So let's think about this. If this is our frame of reference, and it's moving into the x direction 10 centimeters, at the time it hits 10 centimeters, it's also the acceleration of the electric field is going to push it in the y direction, either above or below. So so we have this y formula right here, and it has no v initial in the y direction because it says the velocity is only in the x direction. It starts at 0, so it doesn't have that. So its y final is equal to 1/2 the acceleration multiplied by the time squared. Now we've solved for the time in the previous problem in seconds, and we should use seconds in this part. And here's the acceleration. And the acceleration is negative, and it goes into the negative direction. Because if we go back to the first part of the problem, find the acceleration of the electron. I said that the acceleration was in the y direction. I may have accidentally said that it was in the positive y direction. But I forgot to mention that because q is negative, because it's an electron, because q is negative, it actually goes in the opposite direction of the field. Because the field is in the plus direction, positive, and the electron will go in the opposite direction as it. And you can just use this formula actually. Yeah. So then we know the acceleration, and we know the time squared, and then we'll get this y, how much it travels. And then I think it asks for the answer in centimeters. Multiply by the ratio, 100 centimeters a meter, you'll get how many centimeters. And 35 centimeters into the negative y direction because the electron has a negative charge, which made its acceleration in the other direction. Yeah. So, question number 6, part 1, here. 5.1 nanocoulomb, microcoulomb, I think it's microcoulomb. Yeah, microcoulomb. 5.1 microcoulomb point charge is located at x equals 1.2 meters, y equals 3.1, and negative 3.6 microcoulomb charge is located at x equals 2.2 meters, y equals negative 1.8. Find the magnitude and the direction of the electric field at x equals negative 3.3, y equals 1.2. Okay, so first I want to talk about the vocabulary term point charge. The electric field of a point charge. There are certain formulas which go along with this thing. For example, the first formula is, well, let me go up to, first formula is this one right here. The magnitude of the electric field at a point charge is equal to K multiplied by the Q from the source divided by the distance, or R squared. The second formula is the net electric field is equal to the sum of its parts, and we only have 2 in this case. So I drew a diagram here. Now I just want to say that here's my favorite reference. I just want to say that this diagram is utterly not drawn to scale. Later in the problem, I actually proved that this is not drawn to scale. I must have somehow, well, I guess this is 2.2 and this is 3.1. These distances are this is probably longer than this, Anyway, it's not drawn to scale, but you get the gist of how it's supposed to kind of look. So again, when doing these electric fields, we say this is a positive test charge. This point. So because this is positive, positive likes repel. So this guy is not going to go towards him. He's going to go away. So in this direction, as you can see, and then opposites attract. Plus minus. He's not going to go away. He's going to go towards this guy. So that's the direction of the forces. So this is not drawn to scale at all, but this would be if I did some vector hat addition. So for this, let's break it down into its components. But let's not talk about direction as of right now, because it's easier not to do it initially. Direction. Let's talk about magnitude. So magnitude of the electric field 1, and electric field 1 is from this point, which is plus 1.5 microcoulombs, to the place where we're trying to find the electric field. That is electric field 1 equals a kq over r squared. We know k, 8.99 10 to the 9th Newton meter squared per over coulomb squared. We know q, it tells us it's 5.1. Positive, we're doing positive. It doesn't matter positive or negative because we're taking the absolute value of q times 10 to the minus 6 coulombs because we want to use coulombs always, divided by r squared. And for this, I just use Pythagorean theorem. You could probably figure it out. Pythagorean theorem. So I took this distance, this squared plus this squared equals this squared. Except I don't actually have to take the square root because that's for r squared anyway. So actually I did take the square root, but then I squared it again. So it became immaterial. Anyway, so I get for this one, the magnitude is 1921.5 newtons per coulomb. Let's do the same thing for the number 2, which is from this guy right here, from minus 3.6 to this field. K, magnitude of q over r squared. We know k. We know magnitude of q. Absolute value, we know r squared by similar logic. And then we get this. So now let's talk about direction. Actually, before we talk about direction, let's get the angle. So, of course, I drew this out. This is the triangle there. Solve for this angle, tan inverse, right here. The angle for field 1 is 22.9, right here. And then for field 2, this guy is, from field 2, I'm talking about this angle right here. This guy is 28.6. So that's what I use tan inverse, opposite over adjacent, tan inverse. So direction time. So let's look at this guy. Let's look at this guy, number 1. This guy. Let's E1. It is going in the minus y direction, and it's going in the minus x direction. That's just the direction it's going. And how did I get these directions? Well, I did calculate it in the fact that it's a plus charge. Now, mind you, plus charge or minus charge doesn't make it go into the plus or minus direction. Charge is not a vector, but it's not a scalar. That's what I wanted to say. But charge does dictate the way it interacts with the field. So that's why this vector is in this direction, this vector is in this direction. Anyway, so as you can see, it's going in the minus x and the minus y directions. So minus the magnitude cosine the angle, because it's cosine is x, minus the magnitude sine the angle. For number 2, electric field number 2, the force, as you can see, it's going in the plus x direction, according to my frame of reference, and the minus y direction. So you'll see a plus x, minus y, cosine again, sine again. So if you calculate this out, and you add, you'll get E net is in this direction, newtons per coulomb, of course, newtons per coulomb for all of this. So let's go back to, I just want to show, this is not drawn to scale, because if this implies that it's going in the plus x direction, when in reality, as I've seen from this, it's going in the minus both of them, which means that the net force is, so that means that this is actually shorter. It means it's actually going somewhere here, and it's ending up going like this, which makes sense, because I made this way too long compared to this. So this is 3 point. This entire thing is 3.1. How can this be 2.1? I didn't draw it to scale, which means that this in reality would actually be shorter. So it makes some sense in that area. Actually, I don't think it'll be exactly like this, but regardless, this is the net force the net electric field, my bad. And then we'll find the magnitude and the direction separately because it's easier. Magnitude, take the square of the parts. Direction, so first we'll go magnitude again. Square this square plus this square, square root of that, we'll get this. And then it asks for the answer in kilonewtons or meganewtons or something. What is this? Kilonewtons, that's what it is, per coulomb. So then you just multiply by this ratio. 1 kilonewton has 1,000 newtons, and then you get 1.579. Now, what is the direction? Well, let's go to part 2. For direction, this is E net we found. Theta equals tan inverse y over x equals tan inverse 1142 over 1064. So this is the direction it's in right here. This is from the origin. It goes into this direction, minus 10446 and minus 1142. This is the direction. So if we want to find this angle, well, you can just do simple tan inverse opposite over adjacent. This is the opposite over this adjacent. 1142 over 1046, and then you'll get 47.5. But it's asking for the total direction, so you have to take it into account from this. So you'll get 180 plus this. I'm pretty sure there's another way to directly jump to this angle, but this way is better for me. I think there's another way. So that's how you got that. Now B, find the magnitude and direction of the force on a proton at this point. So in this case, where is it? Right here. We assumed, as we should, that it's a positive test charge. So a proton is positive, so we can just make that, we don't have to change much. Because we know the proton is positive, we know the direction is going to be the same. So first let's talk about the magnitude. So it's at the same point, minus 3.3, 1.2. So the electric field is going to be the same. So this magnitude and the direction of the electric field is going to be the exact same for this proton. Nothing's going to change because it's a proton, it's positive. If it was an electron or something negative, then we would have to flip everything. But it's positive. So we can just use that formula. E equals F over Q. Absolute value first because it asks for magnitude direction. I like doing them separately. You get absolute value F equals absolute value V times Q. We calculated Q, we know Q. It's positive. Actually, we're not even dealing with positive 1.6 times 10 to the minus 19 coulombs. And then we know E from the previous question, or from the previous answer. And I converted it into newtons instead of using kilonewtons because the K constant, and it's just easier in newtons. I think everything should be in newtons. So then we get this. That's the right answer. And then the direction. Since it's a positive charge, the field reacts the same way we know, so it's the same angle. And of course, this is not drawn to scale at all. So it's the same angle, 2 to 7.5. I did not draw, my biggest flaw in this was not drawing this properly. But if you use algebra, which is what we used, we can prove that this is in fact the right way of adding these vectors. So that is the video, and I hope you enjoyed.